So we start by looking at a new example. So we have a file example1.csv. This file I've uploaded to the folder notes and stuff in your e-learning. So if you just open the file, it's a small file. There are only 20 observations. There is a random variable y, which is our y, and there is x1, x2, x3, x4. So p equal to 4 and n equal to 20. So we obviously want to fit y equals beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta 4 x4 plus epsilon, where epsilon is the random error. Usual stuff. The way to do it, I mean we have done this many times. So first you read the data. My data equals read.csv, example1.csv. Then you do fit equals linear model lm. Y follows x1 plus x2 plus x3 plus x4. You attach the data file. After that you print the summary fit, and it prints all the usual stuff. Not much to speak about this, but let's go to the restrictions. So suppose I want to test the two restrictions. The restrictions are 2 beta 1 plus 5 beta 2 is 68.2. 2 beta 3 plus 12 beta 4 is 27.6. If this seems arbitrary, that's because it is. Don't ask me why. Like, why am I doing these restrictions? What's the meaning of that? I mean, don't go into the meaning. Suppose these are the restrictions. That's it. So how can I do that? There are two ways. There's a textbook method and there's the my method. I mean, of course, both methods are based on the same theory. Our math is same, but let's see. So the textbook method is 2 beta 1 plus 5 beta 2. I mean, these equations equal 68.2. 2 beta 3 plus 12 beta 4 is 27.6. Now from the first equation, we see that beta 1 is 34.1 minus 2.5 beta 2. How do I get this? Just take the 5 beta 2 to the other side and then divide by 2. Divide all the sides by 2. That means you express beta 1 in terms of beta 2. Similarly, from the second equation, you express beta 3 in terms of beta 4. And you get beta 3 is 13.8 minus 6 beta 4. So that's the original equation for the model. Y equals beta naught plus beta 1 x1 plus dot dot dot. Which if you write now beta 1, you write it like this. And beta 3, you write it like this. As I've written in this equation, it will become like this. So y is beta naught plus this thing times x1 plus beta 2 to x2 plus beta, like instead of beta 3 we have this thing times x3 plus beta 4 x4 plus epsilon. What I'm doing in the next step is, I'm sorry, it looks like a division. It's not. It's just a line. I mean, sorry, I'll correct that mistake. So what's happening here is, look at the beta 2 over here, and there's a beta 2 over here. So I'm collecting them together. So if I do that, it will be beta 2 times x2 from here minus 2.5 x1. Similarly, if I collect the beta 4 over here and the beta 4 over here, it shall be x4 minus 6 x3. And then this 34.1 times x1 and 13.8 times x3, they come over here plus epsilon. So nothing is missing, nothing is added. But something special has happened. So think about this x2 minus 2.5 x1 is a new variable. think like, let's call it new x2. That's a very bad way to speak about it. People sometimes call it x2 star, but since I cannot, like, okay, I had some problems with that, so I'm calling it new x2. So what's new x2? New x2 is just x2 minus 2.5 x1. And I have new x4. What's new x4? That's x4 minus 6 times x3. Okay. If you ask me the question, where is x1 and x3? They are not. They are not here. It's only x2 and x4. x1 and x3 are gone. Also, you look at this thing lingering over here, and it has no beta with it. This 34.1 x1 plus 13.8 x3 has no beta with it. But we can't ignore this, so let's take this whole thing to the other side. So that means y minus 34.1 x1 minus 13.8 x3. Let's call that new y. So if you do all this, you'll see that the now model is new y equals beta naught plus beta 2 times new x2 plus beta 4 times new x4 plus epsilon. And we can actually do this. So I can define my data $new y. How do I define that? That's my data $y minus 34.1 times my data $x1 minus 13.8 times my data $x3. So essentially I am just doing this equation. Similarly, I am doing this equation and this equation. After I've done those, I do the linear model. So new y follows new x2 plus new x4. The data is my data, but now my data has 3 new variables with it: new y, new x2, and new x4. And after I've done fit2, I'm printing out the summary. In the summary, I can see from this particular column that beta naught hat is 2.1094, beta 2 hat is 10.2078, beta 4 hat is 3.2318. Now I know that beta 1 is 34.1 minus 2.5 beta 2, so the same thing will happen with the hat. Beta 1 hat shall be 34.1 minus 2.5 beta 2 hat, and that's 8.5805. Similarly, beta 3 hat is this particular value. So I have actually done it. Like, we have achieved our purpose. We have found the beta hats. But something remains. We have found the beta hats, but our original goal was to test whether the reduced model is true or not. That means we have to do the F test. Now, let's look at the reduced, like, this is the new model, reduced model. But for the reduced model, the R square is given over here, 0.8404. But this is misleading. Don't go with this R square. There are good mathematical reasons why this is not correct. Not correct means it's not the thing that we want. It's of course correct, but not what we want. So to get what we want, I will just do some calculations. I've done it over here. You can skip if you want. Essentially, I've calculated y hat by hand, typing things by hand, because I have all the beta hats. Then I calculate the SSE, the sum of, the SSE for the reduced model, the SST, the R square for the reduced model, and the R square for the reduced model is 0.8069891. So that's the correct R square. With the correct R square for reduced model, we actually know the rest of them. R square for the full model, the P, the N, and K. So we can now calculate the F by the formula we had before, and it comes out to be 0.3881. The degrees of freedom are 2 and 15. You can check that. So I can either calculate the P value directly, or I can do calculate the cutoff point. You remember, if f is bigger than the value, then we reject. If f is smaller than the value, we fail to reject. So that value is the cutoff point. We calculate the cutoff point as follows, and we see that 0.3881 is smaller than the cutoff point. So we don't reject H0. We don't reject H0 means the restrictions are true. Like the restrictions we had. Which restrictions? These restrictions. 2 beta 1 plus 5 beta 2 is 68.2. 2 beta 3 plus 12 beta 4 is 27.6. These restrictions are true. Now, so that's the textbook way of doing the thing. What's my way? My way is essentially the same kind of math, but you don't have to do all this. So you just have to notice that those restrictions mean Q beta equals C. What's the matrix Q? It's given here. What's the vector C? It's given over here. And with this Q and C, I've written down a function. The function is called new LM. That's not a very good name. The function new LM is written in the file newlm.r. This newlm.r is uploaded in e-learning. So what I'll do is I'll first run newlm.r. So now my new lm function is ready, and then I'll proceed as before. Like, we know how to use the lm function. We say y follows x1 plus x2 plus x3 plus x4. Then we say data equals my data. But now we supply the matrix Q and we supply the vector C. And we get some value fit 3, suppose. Now this fit 3 is something like the original fit, but it's not exactly like it. I mean, it's a much simpler thing. Why is it simple? Because I had to write the whole thing over a single night. It will like take a much longer time and lots of people to create a sophisticated version. But I think it will serve your purpose. So this fit 3 contains many things. If you just do names fit 3, it will give you many things like this. You can explore all these things at your own leisure, but what's important for us is the following. First of all, fit $3 coefficients. This gives you beta naught hat, beta 1 hat, beta 2 hat, beta 3 hat, beta 4 hat. You can go back and check that my values over here are equal to, or at least close to the values from the textbook method. Also, my r square is close to the r square from the textbook method. My f, so for example, if I fit $3, this f underscore rm vs fm. That's a complicated name, but what it means is f for reduced model versus full model. This rm vs fm means reduced model versus full model. And this, it's like the whole thing is f underscore rm versus fm. So if you do that, you will get two values. So the first value is the actual f value. The second value is the p value. If you scroll back, 0.386 and 0.686. Okay, so if we scroll back, this is 0.388. So there's a slight difference because of calculation errors. I mean, the textbook method, the way we did it, will give some calculation errors. So my method is more accurate. And also the p-value is 0.684. So both are close to my answer. And that's it. So once again, this p-value of 0.686 is big, which is good for H0. So we keep the H0. H0 is true. That means the restrictions are true.